I'm going to show you that science is being held hostage by imperfect instruments being interpreted by imperfect human beings. Hello, this is Distinti's Rules of Scientific Acquisition. This is version 5.1, and this is a new rule of acquisition 39, the Instrumentality Trap. 39.0, science depends upon results from imperfect instruments interpreted by imperfect humans. Now, the 39th rule actually is a derivative of the 6th rule and the 29th rule. The 6th rule, prior knowledge trap, basically states that all of our prior knowledge interferes with our understanding of new technology, of new science, of new phenomenon. For example, back in the 1800s, the only thing they knew that created heat or light was fire. And they assumed that the sun was a big burning ball of anthracite. This follows the old phrase, if all you have is a hammer, all of your problems begin to look like nails. And the 29th rule is reciprocal thinking imperative. You should always think things backwards and forwards. In other words, if you take a measurement with an instrument, is what you're seeing an artifact of the instrument, or is it actually an artifact of the subject being measured? Again, you've got to do reciprocal thinking all over the place. So to begin this first example here, what we're going to do is we got this machine. The operators of this machine, the scientists, cannot see into this chamber. What they have in their control room tells them where the hammer is at any given time, and they can move the hammer wherever they want to move it. And then so that what they can do is they can move it around to measure the shape of this test object here, the subject. This is kind of like if somebody blindfolds you and hands you an object and says, tell me what the object is just based on the feel. And that's what it is. They're going to be using a hammer that's instrumented to make measurements to determine what the type of object is they're looking at. And I'm going to use these many simple examples like this to show you how we can misinterpret what we're measuring. So in this example here, because this is an instrumented hammer, what if the hammer were bent? Then, well, the instrumentation isn't going to show you the true location of the head of the hammer. Also, all the measurement devices that tell you what the orientation of the hammer is may have error, may have lag, may have other imperfections or inaccuracies. And so we're at the limit of what the errors and inaccuracies of the instruments are. So rule of acquisition 39.1. All measurements have some form of error and ambiguity. In the next example, we're going to do a high energy measurement. We're going to smack the object we're trying to measure with incredible amount of force. Now, the reason why each one of these pictures look different is because when you're using AI to make the pictures, there's no way to tell them I want it to look kind of like the last one. So forgive me, each one of these pictures, but they're kind of cool. Each are a little different. It's fun. And so what's going to happen is you're going to smash your subject. And then if you go try to repeat the measurement, well, because now you've deformed the subject, you're going to get a different answer. Or in some cases, you're just going to smash it to bits, and it might not even be on the measurement platform anymore. Okay, and so the problem with destructive experiments is that they're going to result mostly in junk. And let me show you a mainstream destructive experiment. When they take a particle accelerator and they smash two perfectly good atoms or protons together, you should not expect that everything that's going to come out of this collision is going to be something real that really exists. Because you're adding energy into this collision, there's a possibility that you're going to synthesize things that don't exist in real life. Now, if we use a watch analogy, if you take two perfectly good gold watches and you smash them together, yeah, you're going to get all kinds of junk and debris. But in a low enough energy collision, some of the parts may pop out that may be perfectly good and in good condition to be put back into a normally good functioning watch. Yes, if you keep your experiment of low enough energy, you can get enough good particles out to say, yes, this was what comprised. But again, you're going to get a lot of debris as well. If you keep increasing the energy of this experiment, these watches will hit together with such force that you're going to start vaporizing and melting and doing all kinds of fusing, and the odds that you're going to get functioning particles out in the debris field of this the odds go down and down that you're going to get functional particles out, functional components out. Okay, so by increasing, going to a bigger and bigger accelerator, I'm not certain that you're going to get anything of any value. You're just going to get a lot of fused together junk that doesn't exist in the real world. In this example here, we now have a ball with holes. But because the hammer head is too wide to fit into the holes, we can't detect the holes. Okay, so what the scientists that are running this machine, what they're going to detect is a sphere that seems to have flat parts on it because the hammer head is flat. And so when they press the hammer against where one of these holes are, it's going to look like a flat spot on the ball. Okay, so all measurements are affected by the nature of the instrument. And the real world example we'll use here is the double slit experiment. So what they do in this experiment is they shine light on the double slit, coherent light, and then they pass that through an attenuator. This is unfortunately a really bad idea. So what they're doing is attenuating the living bejesus out of the light before it hits the detector plate over here. Now this detector plate is powered such that the electrons on this plate are in a very high energy state. In fact, so high that even thermionic energy, thermal energy, is enough to kick one of these electrons off. And those electrons will then go into a microchannel plate. And a microchannel plate is just a way to cascade, amplify a single electron to make multiple electrons. And the output of this cascade plate, this microchannel plate, is a phosphor screen. So each one of these dots are not photons. They're the output of one of these microchannel plates, and these are electrons that strike this sensor here. So the way they have this instrument set up here is they got the light so lowly attenuated that it's just barely above the normal thermionic emission. And this is what they get. And what they do is they keep adding up these plates. They keep taking measurements with a camera, and they keep adding up the plates, the LCD pictures. Okay, and you can see right here what's going on. All these random dots out here are just thermionic emission from the plate. And they have barely enough light hitting the sensor to kick a few more electrons off the plate into the microchannel plate. And so what's happening is they've got a really poor signal-to-noise ratio set up here. And the way we engineers deal with poor signal to noise, and noise, by the way, is a quantum effect. That's a quantum effect of this setup here of the electronic instruments. Thermionic noise is present in all electronic instruments, all of them. And the way we deal with noise in engineering, one of the ways we deal with noise in engineering is we just keep averaging up the measurements, and the areas that are hit by coherent light will start becoming stronger and stronger and stronger until you get this output here. Now we can see other artifacts. I hate this mouse. You can see a line up here. Well, that's a flaw in the plate. You get a little dot here. That's a flaw in the instrument. There's a flaw in the instrument. You can see like a zigzag pattern here. That's probably due to the microchannel plate pattern. Okay, so there's a lot of artifacts in here that are not part of the double slit fringe pattern that are all part of. Even this random noise pattern is part of the instrument. And what they've done is they've attributed this random noise, these random electrons being kicked off, as properties of light, that light's a photon. We can't tell. In other words, if we're using particulate matter, if we're using corpuscular matter to make a measurement here, then of course we're going to view light as corpuscular. Like if you view the world through rose-colored glasses, everything's going to look rose-colored. Well, if you're using corpuscular matter to make measurements, well, your measurements are going to look corpuscular. It may not be that light is corpuscular. We can't tell from this. There's no way you can logically and sanely tell me that light is corpuscular, because, particle, it's a particle photon, corpuscular, based on this measurement, because this is the nature of the instrument. Look at my camera. I took pictures of fireflies. Well, I left the camera shutter open a little bit so you could see the path and the signals of the fire. Sometimes the fireflies blink as they go around through space. And you'd say, oh, wow, look over here. We caught a red firefly. Oh, wow, that's rare and amazing. No. If you blow it up, my friends, that's just a flaw in the image sensor of my camera. There's lots of flaws in the image sensors, red dots and blue dots and purple dots all over the place. Some of these green dots actually may be flaws as well. They may not be fireflies. Again, we can't attribute to our measurement, to our subject, the flaws of our instrument. Here's another example. Same camera, taking a picture of the night sky. The camera is on a tripod. The camera was left open for 30 seconds. That's why all the stars are slightly smudged. If we blow up on a certain portion of this photograph, this is really already blown up here, but we're going to blow it up even more. Again, there's no red flying saucer. That's, again, just a flaw in the image sensor of my camera. The other thing that's important to see is all around here we have all these black dots and all of these white dots. Are these something in outer space? No, they can't be. If they were in outer space, they would be smearing like the stars are. So this stuff here, this again is noise in the LCD of my camera, or the CCD of my camera. Again, we can't attribute the flaws and the noise of our instruments to the subject being measured. And this is most of what my career is about as an engineer, is determining when we make measurements, what is part of the instrument and what is part of the subject being measured. That is half the battle in engineering, is knowing what we can attribute to what. Is it operator error? Is it whatever. Again, I was just going to talk a little bit more about the double slit here. These are just blow-ups of those images. So, if you view the world through rose-colored glasses, it should not be a surprise that everything looks rose-colored. I mean, it sounds obvious, right? So if you make observation using instruments comprised of corpuscular matter, it should not be a surprise that everything seems to be corpuscular in nature, even if it's not. Again, that is the nature of the instrument, and is not the nature of what you're measuring. So 39.4, do not attribute the nature and flaws of the instrument to the subject being measured. In this example here, we have a ball with holes, but now our hammer is small enough that it could fit into the holes. So we're going to detect a ball with holes, but we don't know how deep the holes go, because as we insert the hammerhead into the hole, it's going to bottom out on the handle. So we're not going to be able to know how deep the holes go. And unless we know this flaw in our instrument, we're going to think these are shallow holes and we're good to go, that there's no hole, the holes don't go all the way through, which would be a lie. So we have to be careful that measurements are affected by the limitations of the instrument. In this case here, the holes are uniformly spaced. So if we have a sampling strategy, and again, assuming this hammer fits in the holes, we could actually inadvertently set up a measurement scheme where we measure along the equator and at a certain height above and a certain latitude above that, such that we completely miss the holes. And it would not be, and this happens a lot in engineering, where we set up the instrument and we miss important flaws because we don't look there. Okay, and consequently, the other thing could occur is we may inadvertently set up the measurement so all of our measurements actually hit the holes, and we're going to think we have a smaller ball than we really have, because we're going to bottom out when the handle hits the side of the sphere. Okay, so we have to be careful when we set up. We need to put a couple of random measurements. If we're going to take a uniform measurement, we got to put a couple random ones in there just to make sure that there's no gotchas. See, all measurements are affected by the sampling strategy. And sampling strategy is dictated by imperfect human beings. And what if we had a big wad of cotton candy and we're trying to measure it with our hammer? It's very likely that the cotton candy is not going to set off the pressure sensor on the hammer, so that we're trying to make measurements and tap it against the surface, that we're going to ever see that there's anything there. So we may actually end up with a null measurement, where the scientists say, you've tricked me, there's nothing there. And the real-world example of this is the Michelson-Morley experiment, where we set up an instrument to measure the ether. That instrument detected a null result. In other words, and they assumed that there was no ether. That was a false assumption, because the Lorentz-Fitzgerald contraction equation says that the experiment would necessarily length contract along the direction of its motion through the medium, which means that the null result of the Michelson-Morley experiment is the expected outcome. It doesn't mean, it does not prove the ether is there, but it doesn't disprove the ether either. Keep that in mind. We got to be careful about what assumptions we make. And again, this goes back to the sixth rule of acquisition, where our prior understanding of things will affect how we interpret the results. And one of the biggest problems in scientific measurements are human beings. Consider that we have governments bankrupting themselves right now to make weapons of war, and virtually no money is being spent battling cancer, finding a cure for cancer. I would think more people die from age-related illnesses and cancer than die from any other cause. It just blows my mind how silly of a species we are. And the other thing is, you consider that we have entire call centers dedicated to cold calling old and infirm people, trying to scam them out of their life savings. And then you've got phishing scams, scam after scam after scam after scam. Everywhere you look, it's a scam. And if you look what's going on in China, how they're scamming each other, it's really sad. You wonder why aliens do not want to come down and visit us. So I'm sorry, there's no issue with the Fermi paradox. If I were an alien, I wouldn't want to come anywhere near this planet. The scams are rampant in science as well. So you cannot trust journals anymore. They just publish stuff that their readers want. They're just like any other media producer. They're producing what they need to produce to get the clicks, to get the subscriptions, to get the income. The truth be damned. So 39.8, human interpretation of experimental results are problematic. This is just a recap of what we went through. I'm not going to read it to you. This is the Patreon site. This is the best way to support this program. $5 a month ain't going to kill you. This is the repository. The means of how you would navigate this are found at the YouTube channel, at the introduction. This is the YouTube channel. That's etherealmechanics.com. This is the blog site. Big shout out to Sebastian. Again, if I can find more time to visit the site more often, I will. I'm trying to come up with a way to reduce my JOB, but we'll talk about that not in this format. Thank you. No more voodoo physics.